parabola time. So we have two parabolas here. And we're not given any numbers. That's because we're in an algebra paper. So here we're given the first one, that looks familiar, right? ax squared plus bx plus c. The second one has the same plus c, but a different value than a and b, in this case d and e. And all it says is that they're constants. So in fact, they could be the same. We don't know. But this problem is asking us to investigate, all right, we want these two parabolas to meet. So by meet, right, we mean they intersect. However they do, it could be positive parabolas or negative parabolas. But we want to find out the conditions or the restrictions so that they will always meet at two distinct points. So let's just have a think of what that could look like. So if we have a parabola like this and this, I guess a question for you, will these ever touch going up this way? No, they won't. So actually there's only one distinct intersection point in this example. Another possible situation could be a positive and a negative parabola. In this case, they do intersect each other at two distinct points. But notice if this negative parabola was shifted to the right, they wouldn't. Right, so there's only certain situations that they intersect at two distinct points. So where to begin? Well, like we just did, have a think about the problem first. What could that look like graphically? And now we can just focus on the algebra. So they will meet or they will intersect when y1 equals y2. Right? For two functions to have an intersection point, they must equal each other. So we can write that as ax squared plus bx plus c must equal dx squared plus ex plus c. Now, will this be one or two distinct points? We don't know, right? We haven't got that far. All of this is saying is that we're looking for the intersection points between these two parabolas. So from here, we could simplify it a bit. I notice plus c on both sides and get rid of those. We could group like terms. So the ax squared minus dx squared, so I just took this across. Similarly, plus bx, and I'll subtract ex on both sides, equals 0. So looking at these first two terms, I could write that as x squared, a minus d. And the second term could be x, b minus e. Right, so I just pulled out the x squared and the x. And then finally I look at both of these terms and I see they have an x in common. Yep. So we essentially just group like terms, factorize once, factorize twice. And we did this so we could look at like possible restrictions on A, B, C, and D. We actually eliminated C, so that tells me that actually it doesn't matter what the value for C is in this problem. But now here, it's a quadratic, right? And we can solve for the brackets, the terms inside the bracket. So either x equals 0 or this whole expression equals 0. So x so I just subtracted b minus e from both sides. Now we can divide by a minus d. And actually in the numerator there, I'll just distribute that negative sign. So it'll become e minus b. Just makes it look a bit neater. Don't strictly need that. Now what this is saying is the two x values of the intersection points are either 0, so that's on the y-axis, or at this value x equals e minus b over a minus d. So one solution always on y-axis, so that's when x equals 0. Okay, and then the other solution for the other intersection at x equals e minus b over a minus d. Great. And remember, this problem asks us to have two distinct intersection points. So it's always going to be at x equals 0. That's great. That's a free one. But there are some times, like for certain a, b, d, and e values, that we wouldn't get one here. So have a think. What would make this expression here, give us 0 or be undefined? Right? If it's 0, we already have a solution at 0, so it's not distinct. If it's undefined, then it's not a solution, and we still only just have one solution at x equals 0. So this cannot equal 0, and has to be defined. So if it cannot equal 0, that means the numerator can't equal 0, which means e minus b can't be 0, or e can't be equal to b. Right? If they were equal to each other, the numerator would be 0, and we don't have two distinct solutions. For it to be defined, the denominator can't be 0. Right? If we divide by 0, we have an undefined number, which means a cannot be equal to d. So in summary, we have two parabolas. We're looking for the restrictions to give two distinct intersection points. So we equated them together, we simplified, factorized once, factorized twice, solved for the solutions, right? Solving for x. One of the solutions we found was the y-axis, which is pretty straightforward. The other one was in terms of e, b, a, and d. So we had to think about, all right, when will this equal 0? Because that's not a distinct solution. Or when will this be undefined? Because then it's not a valid solution.